Alright, hello. This is our machine learning final project. We are the deep learning for disaster tweet classification group. I'm Kurzwa. I have Jonathan and True with me.
As we know, social media has become popular than ever. It is the place where people share many things like photos, places, memories. Some platforms are used to alert disaster around the world. It spread news spread sooner than television and can provide life-saving aid. It's one of the largest social media platforms. Twitter has around 650 million users in 2025. The speed people retweet is very fast, 51% in 1 minute, 60% in 30 seconds, and 90% within 10 minutes. These advantages make Twitter the perfect choice to train AI model for early warning application. And our goal is classify tweet as disaster related versus not related. We compare two models, the traditional one based on logistic regression and a transformer model based on BERT. We analyze pre-processing, model performance, training challenges, and possible feature improvements.
So some challenges we had while making the project were file permission errors. We had some installation issues. When we were working on the project for the first time, we had some long times on the CPU because of how BERT trains. Very large vectorization matrices for the LR. We had some GitHub repository issues. We fixed that though, and there were some different challenges because some I worked in VS Code and we also used Jupyter Notebook, but there were some issues on both the HVC and VS Code. I personally had some issues with file permission errors. It was because of the file from the .csv file, and some installation issues because I got path errors and my Python interpreter was set to the wrong one.
So the data we use is from Kaggle. Then the data set is named disaster tweet. It has 11,000 tweets with 5 columns. Save as a CSV file. The 5 columns are ID, keyword, location, text, and target. However, we only focus on text and target column to train our model.
And for pre-processing,
For oh, sorry.
yeah, for pre-processing, we went ahead and removed the null or invalid text and things like URLs, emojis, special characters. We went ahead and combined keyword and text for better context. And our tokenization methods for logistic regression, we use the count vectorizer, the TF-IDF to transform our words into numbers. And then for our BERT model, the BERT tokenizer, we use WordPiece. And for our training and validation split, we did an 80-20 stratified by label on our logistic regression model.
Alright, so here's our baseline model. Uses logistic regression. We had a validation accuracy of about 78%, and it was basically just for comparison for the BERT model. For the for the first run, it performed real well. It had a 70-20 split, and it was finding non-disaster tweets with an F1 score of 92%, and it was okay at finding disaster tweets at 67%. And for our second run, we used the baseline model. Um, we used the baseline model. It improved with an 80-20 split, and the F1 score improved for disaster tweet detection by almost 1 point. And all the stats, actually, the micro average and weighted average also improved slightly. And for so why BERT? Why do we use BERT? It reads tweets in context, understands meanings, not just words. It's good for short, noisy texts like Twitter. Specifically, we use BERT-based unclassed. This is information about specifically the local one. We use 2 training epochs on the first run. Had a learning rate of 2E-5 and had a set batch size of 8. And then here's the results for the local run. It had a really strong performance for only 2 epochs. The accuracy is higher than the LR baseline. It generalizes well, and the only issue was the training was extremely long. It was around 2 hours per 1 epoch, so like 4 hours. I had a moment there where I thought it wasn't working just because of how long it was taking. And then also some charts that were generated.
And then from this point, we were to take it to the HPC and test it there on the TAMU launch cluster. And so there, for some fine tuning and hyperparameters, went ahead and set the seed to 42, and this helped our results be reproducible every time we run the model in the future. And I also went ahead and changed the learning rate. I lowered it from 2E-5 to 1E-5. This helped improve the model as well, and also increased the batch size to 16. So these are the best results for our transformer model. At the last epoch there, you see the lowest training loss at below 10% there, 0.02, and then value accuracy at 0.92. So the model was learning really well, and was able to distinguish between disaster tweets and non-disaster tweets pretty accurately. And so here's our results in comparison to our logistic regression base model, which had the accuracy of 87%, and to our transformer model best score of 92% accuracy. And you can also see the precision, recall, and F1 scores as well. And so there you go.
Let's do the comparison between 2 models. Logistic regression, the model is fast, simple, cheap to run, the training is minimal, and the interpretation is straightforward. It serves as a baseline. However, it has no mechanism for contextual understanding. It fails on ambiguous words and the performance degrades. About the first transformer, it has higher accuracy because it uses context, relationship between words and cues. It handles well on slang, sarcasms, and ambiguous text effectively. The cost is computational. The training is slow. GPUs is needed for better performance, and the memory is significantly higher. Conclusion: reprocessing and factorization increase the baseline model efficiency, whereas contextual modeling produce highest accuracy across all tasks. Using the local machine and high-performance computers resources expand the range of experiments, enabling larger models and faster training cycles. The resulting system supports real-time disaster classification, reduces misinformation flow, and accelerates response actions for emergency situations.
For team contributions, I mostly did model implementation. I worked and updated the pre-processing, vectorization, and the BERT training code. I'm mostly the one who worked on local train experiments, and I helped with the majority of the slides.
And I handle the documentation and write the report for the team. I also contribute to the slides.
And I trained the baseline logistic regression model for our data set, and I also did the HPC plus advanced model testing, setting up and configuring the HPC environment for training, trained the transformer model in the GPU cluster, and did the hyperparameter tuning. And that is the end of our presentation. Thank you, and feel free to reach out to any of us if you have any questions. And take it easy.